All right, welcome everybody to a new week of Discrete Math. We're going to continue our discussion of recursion today. And if you have any questions about Markov chaining, let me know. So where we left off last time was talking about the things you need in order to get a good recursive function, right? You got to have a good base condition that can handle the end zone, and you must always move towards the end zone. So in this case, we have a good implementation of Fibonacci, but the performance is sort of explosively bad. I'm not streaming? Oh, that's right, I left and rejoined. Okay, there we go. Usually if you don't plug yours in, yeah, it was plugged in. I didn't do anything to it. I left and rejoined, and all of a sudden it started working again. Yeah. Okay, so you guys remember the two things plus, thinking about the recursion depth limit also kind of matters, like in a practical sense. Like if you're going to be using recursion to print out a vector, then just be aware you're not going to be able to use recursion for very large vectors. All right. So, 10 people streaming right now. What happened to the rest of everybody? Okay. So you want a correct algorithm, and this is one of the best things that I learned in CSI 26 when I took it, which is the notion of being able to prove code to be correct. And that's an odd notion. Okay? It's odd. The notion you could prove that your program is correct for all possible input. Like, how the hell do you do that? It seems impossible. But you can do it. Okay? So there's something called a proof by induction, which we're going to talk about. And the way the proof by induction works is you prove that it's true for the base condition, and then you prove that it is true for the inductive step, basically. So for all input, the base condition must work, and it must move towards the end zone, and it must be correct along the way. So proof by induction is the proof of computer science, in the words of Edgar Dijkstra. All right. Is recursion actually practical? See, here's the thing. Like, I don't really care if it's practical or not, because when you start thinking about, like, correctness and proving that your code's correct, then the thing all in caps there starts becoming a lot more important. So proving that for all input your code works, right? So don't forget about negative numbers. Don't forget about large positive numbers. You know what I mean? Don't forget about edge cases. That mindset of being able to handle anything that gets thrown at your function. If your function says it takes an int, it'd damn well better take an int, and not just like positive ints. You know what I mean? If your code explodes on a negative number, then you weren't really wanting to take an int as input, right? You wanted to take an unsigned. Yeah. Okay, so you have to make sure your code works right for positive numbers, negative numbers, zero, edge numbers, large numbers, very small numbers, that kind of stuff. Oh. And it'll give you the right answer every time. Oh. And so when I took this class, which was 2 quarters of discrete math, 20 weeks, we didn't do any programming at all. But what I found was after the 20 weeks were over, I was writing much better code than before. I was writing code that didn't have bugs in it, right? Generally speaking. Before, I just sort of like throw some paint at the wall and see if it worked, and if it didn't work, then I'd change something kind of randomly and then see if that one worked, and afterwards I started thinking about my code in a much more systematic fashion. All right, so let's go through this with a famous algorithm called Mergesort. Okay. So Mergesort is a great sorting algorithm. It's very easy to write. It's provably fastest running time as far as like big O goes. There's like 4 or 5 algorithms that are commonly used that all have order NlogN performance. You guys know that order NlogN is the fastest sorting function you can have for random data. You guys remember that from 41? Yeah. Pepper charm. It's also a lie. Well, it's a lie if it's not random data, right? So, if, for example, all of your numbers are from 1 to 10, you can do what's called Radix Sorting, which is faster than order NlogN. Do you guys want to see Radix Sort? I can code it for you real fast. Power of coffee. Activate. Okay. It's a cold morning, isn't it? Actually, gonna turn my heater on. It's 47 degrees when I took my daughter to school at 7:50 in the morning. So your basic sorting is going to be something like this, right? So while true, so we'll read one integer at a time, and if x is 0, we break. Otherwise, we add it to the vector. Are you guys all familiar with this code? Hopefully. Okay. So here's your basic sorting function. And what kind of sorting does it do? It can do any order NlogN that meets the constraints. So we actually don't know, just from our perspective here as a user, which kind of sorting is actually going on here when we call sort. It'll probably be quicksort, but it doesn't technically have to be. There's other sorting algorithms that work. Okay, so if we compile this code, then we get it sorted. Oh. It's order NlogN, right? Now, it's traditional sorting, right? What if I did this instead? Okay, so there's a little bit more for me to do here, but you'll see the point. So let's add some 1s, some 9s, some 5s, 4, 3, 2, 6, 7, 9, 1, 0. And you'll see here what it's printing out is the count of this. So what it's, I'd add one more line, but it'd print out 1, 1, 1, 1, 1, 1, 1, 1, 6 1s, 1, 2, 1, 3, 1, 4, 5 5s. You see that? No, this is not stall sort. Stall sort's a joke, where you shoot any object that's not sorted. What we're doing here is we're counting how many times each integer appears. You see that? So it's like a hash table. So if we read in a 6, we go to bucket 6 and increment its count by 1. If we read in a 9, we go to bucket 9 and increment its count by 1. And then we go over the entire set of buckets, and I'll do it the proper way for so for every bucket, okay, so for every bucket, if we have a count of 5, we'll print out that bucket's labeled 5 times. So if we're at the bucket for the number 7, and there's 3 in the bucket for 7, we print out 7 3 times. Okay? Okay, so if I type in 6, 2, 3, 4, 5, it prints out 2, 3, 4, 5, 6. All right. What do you think? What we're doing here is we're counting how many of each input we got. How many times did we get a 7? How many times did we get an 8? How many times did we get a 9? And this is order n sorting. And then it is going to be order m printing. Okay. What is m? So anytime you have something that's order n, by the way, it basically means that it's free, because we actually don't even need this vec thing up here. We can actually just do this while we're processing the input. And anytime you have a function that takes input, it's got to touch each element in it at least once, right? So the sorting is actually essentially free, because you've got to at least read the data in to do anything with it. And so we could just put the things into buckets. So every time we get a 7, we're like, all right, increment the count in bucket 7 by 1. Get a 3, increment the count on bucket 3 by 1. And you don't even have to make a vector at all. This approach up here takes order NlogN time and order n space. Okay. So this algorithm, or traditional sorting, requires order NlogN time to sort it, and requires n space. This one actually doesn't require any time at all, really, to do the sorting, because we can do it up top here. So we have a requirement of order M space and order M printing. Okay, what is order M? And this might give you an idea of why people don't use Radix Sort. Because technically the sorting is almost free. What is M? Mega? It's a different number. Just like how n represents sort of the number of elements we're processing. What is M? What is it proportional to? It's a good algorithm. Memory? The count? What is the running time proportional to? Look at the code. What is the code proportional to? N cubed? Order n plus n printing. Will that give you some clue? It's the size of the container, exactly. So when we do radix sorting, if you know the numbers are all going to be from 1 to 10, then you make 10 buckets. You make essentially a hash table of size 10. Every time a 10 comes in, you increment bucket 10 by 1. Every time a 7 comes in, you increment bucket 7 by 1. What happens if 40 comes in? You don't have a bucket for it. You can't sort it. So Radix Sort is the running time is proportional to the number of buckets you have. It's n. In time complexity, we use n usually for the size of the problem, and then m usually represents something else, some other variable that matters. Because in this case, the sorting is basically free. The sorting is free, the printing is free because they're both order n, and you have to, you have to read every element and print every element, and so there's essentially no cost to that part. But there is a very big cost if you are talking about using Radix Sort for like integers. Like if you want to be able to sort any integer, how many buckets would we need? Infinite? Well, let's say we're talking about ints in C++ on the server. Yeah. We would need 4 billion buckets. So we'd have to allocate 16 gigs of RAM to hold it. And then every time a number came in, 3,242, you go to bucket 3,242 and you increment it by 1. And then you get 1,331,000, you go to bucket 1,331,000. The negative number is you probably add negative 2.1 billion to them. And give them their own buckets. And then when you go to print, you iterate across every bucket you have. And for every bucket that has a value in it, you print out the it's the label on that bucket that many times. So if bucket 7 has a count of 3 in it, you print out 7 3 times. 7, 7, 7. Okay? So do you guys see why we don't use this for ints? Despite it being technically faster, because it's not random data. Integers are a finite, there's a finite size for integers. So technically we could sort ints. Not all integers, but ints, you know, from negative 2.1 billion to positive 2.1 billion. We can sort them in order n time. You guys see what's going on here? That's the sorting. We're just counting. We're counting how many of each. You know, if we grab a 42 from there, then we go to bucket 42, and we increment its value. What do you guys think? What's your opinion on the sorting algorithm? Good for small numbers, bad for big. Yeah, that's a good way of putting it. Technically, it's faster than sort, just in terms of, you know, if the size of the problem essentially is like unbelievably massive, then Radix Sort will actually win even on its, right? Like we're not just talking like 2 billion numbers to sort, but like 100 billion. You know, randomly scattered across negative 2.1 billion to positive 2.1 billion. Radix Sort will actually be faster. Then it'll actually probably take up less RAM. Because we technically don't need this, right? We can actually just do the counting. Every time we read a number, let's just do this. Get rid of you, get rid of you. Let's make it a vector of unsigned ints, just to not have to worry about negative numbers, right? It's not very good at handling all input. I mean, yeah, all we have to do is make this number, you know, $4.2 billion. So if we had 100 billion integers coming in, unsigned integers, to just make our life easy, this will actually beat your regular sorting. Because regular sorting will need to hold all of those 100 billion integers in RAM. We're discarding them. We're not holding them in RAM. This code, Radix Sort, this will always have a fixed RAM cost of 16 gigabytes. Okay. And it will always have a cost of basically M. It's order 4.2 billion. It's technically constant running time almost at this point to print it. So the algorithm is essentially free. As long as you're willing to have a constant running time of 4.2 billion. So I put an M there. M is the number of buckets you have. So it's not N that's the problem with Radix Sort, it's M. It's the number of buckets you have. It's the range of values that you have. Make sense? And I'd have to look up the actual. There's silence on Discord, so I'm just gonna sit here and wait for you guys. Do you understand this, or is it too baffling, or too early in the morning for you? It's a really cool algorithm. Okay. So yeah, if you ever have to sort like 100 billion integers, like the RAM cost is 16 gigs instead of 400 gigs. The running time is essentially free at that point. Sorry, it's not n plus m, it is n times m. Sort of, yeah. Well, yeah. No, not really. It's more or less proportional to the number of buckets times the average number of elements. It'll work out to be order m. Yeah, it's basically n plus m, actually. Just call it that. Okay. So if n is smaller than 4 billion, then you're going to be wasting way much time printing out all the buckets that are empty. Okay, so that is Radix Sort. So Radix Sort does not work on random data. Random data means the values could be literally anything. Think about, for example, a big int. If we were sorting big ints, then big ints don't really have a maximum size. So you can't use Radix Sort to sort big ints. Does that make sense? But it's really useful. Like if you know something about your data, you can beat the provably best running time. You guys with me on this? So when I say it's the provably fastest, there's a couple really important caveats on it. That you get greater than or less than using like the less than operator. Basically, if there's some other method that's possible, you maybe be able to beat this. If it's not random data, like if it's the numbers from 10 to 20, then there's faster methods as well. Okay. You guys all cool? Understand the principle? Okay. Merge sort. So merge sort, we have a base condition on merge sort, and the base condition on merge sort is stylus go. Yeah, it does really matter right now. I need to find that. And the base condition is sorting an array of size 1. Yep. So here's the base condition. If you give me an array of size 1 that's got some number in it, is that array sorted, yes or no? What do you think? Is it sorted from least to greatest? Okay. All right. I agree too. I concur. If you give me an array of size 1, technically an array of size 0 is sorted also. Right? Yeah, you hand me an array of size 1. Yep, that looks sorted to me. Yeah, no work necessary. Done. Return. Okay. So, what if you give me an array of size 2? It's got like 42 and 7 in it. Then what we do with merge sort is we split them to 2 halves. We sort the left half and the right half. Done. It's size 1. They're sorted. And then we merge them together. That's why it's called merge sort. So we do something called like a zipper merge. Like on the freeway, And when you merge sorted, if you have 2 arrays that are sorted, you can merge them together in order n time. So if you have 2 sorted arrays, you can merge them together in order n time. And so I'm going to merge these together like this, 7 and 42, and we're done. Okay. If I had an array of size 4, Found an array of size 4. Boring color. Galaxy pen. Toss me out some numbers. If we have an array of size 4, then what we do is we split it in half and split it in half. Right? So left half is 12 and 56. The right half is 6 and 42. And then, because these are not the base condition yet, we split them again. 12, 56, 6, 42. Okay, and so we split and split and split and split and split until we get down to the base condition. Okay, so phase one is split. Okay, until you get down to the base condition. Now all of the arrays are sorted, right? Merge sort is very much a recursive algorithm. Yeah. So, split them all down, and then we merge them back together. So we do a zipper merge, least to greatest. Phase 1 is split. Phase 2 is merge. And so we zipper merge 12 and 56 together. We merge 6 and 42 together. Then we merge these two together. So when you do a zipper merge, let's go into that a little bit. We want to find the smallest number across. We have n elements over here, right? Across the whole thing. How many comparisons do I have to do to find the smallest element across all n of them? How many numbers do I have to look at? Do I have to look at all of the numbers, or do I only have to look at 2? Let's talk about zipper merge. I've got here n elements. I've got n elements. How many elements do I need to look at? If I've got 2 sorted arrays, these are both sorted arrays, right? This isn't random data. They're sorted at this point. Remember? Because we split them down until they were size 1. Size 1 is sorted, and then when we zipper merge them, they come out sorted. Okay, so we're always merging sorted arrays together. Yeah, there's only 2 elements we need to look at. We need to look at this one and this one. Which one's smaller? One. Okay. We move the pointer. It's probably just an integer, right? Which one's smaller? And OneNote did its thing where it stops responding to input. Fantastic. So yeah, 3 smaller. And so, you guys see how this algorithm works? What's smaller? Okay, and so we just keep doing that. Mark them off. What's smaller? At any one point, you're just checking to see between the first person, right, in each one. So in this case, 5 smaller, 7 and 8, 7 smaller, 8 and 9, 8 smaller, 9 smaller. Stop moving that. I think you guys got the idea now. 40 is smaller than 200. 100 smaller than 200. And 1,000. And 2,000. Okay. And there you go. What do you guys think? So a merge is an order n operation. Right? So if we are handed two sorted arrays, we can merge them together in order n time. Does that make sense? Okay. So, so this becomes 6, 12, 42, 56. Okay. So that is order n work. So each merge is order n work. How many times do we have to do a merge? So when we merge all these size 1s together into size 2s, that's order n work. We then merge all the 2s together into size 4s, that's order n work. If we merge all the 4s into 8s, merge all the 8s into 16s, all the 16s into 32s, the 32s into 64s, 64s into 128s, 128s into 256s, 256s into 512s, 512s into 1024s. It's doubling in size every time, right? So how many merges do we have to do? Anytime you have an exponential thing like that, it's going to be log. So every level of merge sort we have is order n work, and the number of levels we have is log base 2 of n. So how much total work are we doing? If we do order n work per level, and the number of merge, basically all the merges consume order n time because it's the whole array we're going over every time. We're going over the entire array every time, merging them from groups of 1 to groups of 2, groups of 2 to groups of 4, groups of 4 to groups of 8. Because it has that exponential growth property, the number of levels we have to do is the log base 2 of n. Right? If we had an array of size 8, we split 8 into 4s, into 2s, into 1s. So there's 3 levels. Log base 2 of 8 is 3. Yeah. So the running time of this is order n log n. It's a very easy algorithm to write. You guys want to see me do it? Or do you want to do it? Why don't you guys try to do it? I'll give you guys, how long do you need? Like 5 minutes? Just so you know, there is a standard library function that does the zipper merge. And that's usually the hardest part. Where are you? It's called merge. Yeah. So you pass in vector 1.begin, vector 1.end, vector 2.begin, vector 2.end, and then a pointer to some vector that you're going to be writing into. Yep. So if you got a vector, and if you've got 2 vectors and you're going to be writing the results into here, then you say merge from, I don't know whether you're using int array, but it's going to be, if you had a vector, it'd be first.begin, first.end, second.begin, second.end, writing into vector.begin. It's a pointer to the beginning of it. It looks like the memory has to be allocated already, and then it will merge the results of these into the vector. Okay. So how long would you guys like to have to write merge sort? Ten minutes? 20 minutes? I'm serious. You guys should just write it right now. You've been very quiet today, so rather than me doing it, why don't you guys do it? Get your programming juices flowing. 20 minutes. Okay. And then we've got a break coming up too, so it's 11:20. Okay. Begin. Sorry about that. Show me what you got. Post your screenshots, please. We're very close to having working implementation here, actually. The approach I took was to pass the vector in by reference and pass in the beginning and ending part that we're going to be sorting. And then I figure out where this is the end of the first half and the beginning of the second half. It's basically halfway in between. And I pass that to a recursive call, that to a recursive call, and right now I'm just printing out the ranges that it's printing over just to make sure that it all works right. So it'll sort from 0 to 6, which splits into 0 to 3, which splits into 0 to 1, which splits into 0 to 0, which is size 1. Then the right half of that is 1 to 1, so 0 to 1 splits into 0 to 0 and 1 to 1. Then 0 to 3, so then we're on 2 to 3, splits into 2 to 2 and 3 to 3, 4 to 6, which splits into 4 to 5, 4 to 4, 5 to 5, and 6 to 6. So yeah, so this is the approach I always take when doing coding, is before I get too far into it, I just want to make sure, like if I'm doing something a little bit tricky, you know, my brain's not always confident that the algebra works right, or that, you know, if it's not an exact power of 2, then there'll be gaps in it somewhere or something like that. So yeah, I just like printing out all the things and just making sure that the ranges work. Am I still muted? Can you hear me? Hello? 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 It's showing I'm broadcasting on here. Okay. So post your screenshots. I want to see what you guys did. I'll pause it. I want to see a screenshot from everybody. All right. Let's finish merge sort. So after we make this call here to merge sort, the left half of our array is now sorted. After this call, the right half of our array is now sorted. So we need to zipper merge the left and right halves. So we'll make a vector of, what are we doing? Vector of ints, vec. And we need to merge vec dot begin plus begin, vec dot begin plus mid. No, that's not correct. That's going to be an off by 1 error. Because iterators are supposed to be 1 past the end of it. So we need a +1 there. Vec.begin plus mid 2 +1. And vec.begin plus end. The beginning, and then that's the end. And then we're going to write this into vec dot what was it? Vec dot back. What was it? Back inserter. Oh, we already got vec, huh? And then, so this is going to do a zipper merge between the two halves of the array and write the result into temp, or it might, I don't know. There's a lot of algebra in there that I haven't tested yet. System pause, are you doing Visual Studio? Interesting. And then we just need to copy those values back into Vec. See how that goes. Yeah, there we go. All done. That's merge sort. So, your next homework assignment is to write merge sort. So all of you that were just copying my code, you can copy my code. I guess. Don't just copy my code. I won't give you credit for it if you just copy my code. But your assignment is to do code golf on it. Minimize the number of semicolons you use in your code. Okay. So you got to rewrite this code using as few semicolons as possible. Can you do it the way you did it, or do you have to write the sort? You have to write the entire function. It's got to take in, it's got to look exactly like this. It's got to take in, you can't mess with main. It's going to take in a vector and take in a couple of parameters as far as which range it has to sort, and then it's going to recursively call itself over and over again. Okay, so this is what merge sort looks like. You split it in half and split it in half, split it in half, and then once they're all split in half, so they're size 1, these are sorted, and we zipper merge them together. And when you zipper merge them together, they're now sorted. And so when you zipper merge these, they're now sorted. And so this function here looks kind of gnarly, but it's basically saying sort the left half and the right half, do a merge between the left half. How many people know what that means, by the way? Let's go over that. Let's try to explain this a little bit. You can't call the sort function, by the way. You have to actually write, merge sort. How many people know that that's doing that? What happens when you add to an iterator? You guys are just like need more coffee today or something. It's like been very quiet on Discord. That's the iterator to the front plus and value begin. That's correct. What does it do? What is that returning? If I were to cout vector.begin plus 3, dereference it, what is this going to output? The third element? Or the fourth element? Or the fifth element with Lilu? 10, 20, 30, 40, 50. It prints out 40. It's the fourth element. Okay. Because the way iterators work, I'll go over these again because they are worth going over again. Let's get too hot in here now. But good guess, Tomas. Thank you for participating, by the way. Because there's like a lot of people on the chat right now that have not said anything all class. I can see you, you know. I can see you. So, So if we have a tablet, isn't working. All right. So if we have a vector, let's go over some basic C++ here. There's a vector called vec here. It's got a size of 4. Vector.begin is a pointer. It's actually something called an iterator, which is a like a pointer. It has the same syntax as a pointer. It's a little bit different. It's a class, for example. So vector.begin is an iterator pointing at the first element. This is vec.at0, right? So what happens if I add 1 to an iterator? If I add 1 to an iterator, it now points here. If I add 2 to an iterator, if I add 3 to an iterator. Okay? And so these types of iterators, you can do arithmetic with them, and every time you add to them, it moves them one spot further in the array. And so if I were to say sort this array from vector.begin, like if I said sort from vector.begin to vector.begin plus 3, which elements will be sorted? So sort from vector.begin to vector.begin plus 1 plus 2 plus 3. It will sort these 3. It does not sort 40. Good guess, though. Because the way that end pointers work, there's, in pretty much every standard library data structure, there is a special sentinel value, is what it's called. And vector.end actually points here. So when you say sort from the beginning to the end, end is not pointing at 40. End is pointing at 1 past the end of the array. So when you say sort from vector.begin to vector.end, it will sort all of the array. And the reason why it does that is because sort uses the half open range pattern. So if you guys have seen this pattern in algebra, like if you have a number sequence from 0 to 6, but it's like that, that means the number's from 0 to 5, not including 6. Okay, and that is the same half-open pattern we use in for loops, right? We'll say for int I equals 0, I is less than 6, I plus plus. This is why in C/40 I told you to always write your for loops this way, because it matches how we do everything in computer science. Or at least in C++ world, we always use the half-open range pattern like this, where we sort up to, but not including, vector.end. So if we say sort from vector.begin to vector.end, it sorts from the beginning up to, but not including the end. Okay. Or if we're working with vectors, we sort from, or if we want to print all the elements in a vector, we'll say for int I equals 0. I is less than vector dot size, right? I plus plus. You guys with me on this? For int I equals 0, I is less than vector dot size, I plus plus. Less than, not including. Why? Because vector dot size is 0, 1, 2, 3, 4, right? And so the same pattern that we use everywhere in computer science, we use also in the standard library when it comes to sorting. And so that's why I was adding these plus 1s here, because I actually want to sort it from the index held in begin to the index held in mid. In order to do that, I have to add 1 to it, because it goes up to, but not including that point. So I added 1 so that it would sort from the beginning to mid, or do a merge sort. And then here it sorts from, or does a merge from mid to end. In this case, end is the last element. It's not 1 past the end. That's why I said it's an inclusive It's an inclusive, not a exclusive with a smooth parentheses. Yeah, off-by-one errors are the bane of computer scientists. Okay, so yeah. So do you guys understand this notion? How you can like add a number to an iterator, and it just moves that many elements down the array. Okay. Cool. Very useful stuff. Especially when you work with a standard library. So your next homework assignment will be pushed out now, and you have until next Tuesday to do it. Why? Because there's Mergesort. It's done for you. Sudo deploy homework CSI 26 Mergesort golf. And so the what? I still have a homework assignment. Yeah, I know. This one's easy. I've literally given you the answer. So yeah, look familiar? All right. So your code has to be correct. It's got to sort things properly. Okay. You can only edit things between the begin and end marks, right? You can add a helper function if you want, if you think that'll help you. You can't mess with me. Basically the same rules as before, except this time you're being counted on the number of semicolons you use. Okay, so you have to minimize the number of semicolons. Oops. So semicolons within here count. Semicolons down here do not count. Okay. So yeah, I'm basically giving you all a C on this assignment to begin with, because I've literally given you the code. All you have to do is type it up. You're done. Now, how many strokes was my code? Let's find out. Eight semicolons. So starting off by giving you guys a 9 out of 10. That's too easy. You can't use my code. Everything within the curly braces there counts. Okay? So don't turn in my code. The cheat checker will pick it up. I want you to write it yourselves. You can't just change the variable names and stuff like that. Okay? So, yeah, the points are based on the number of semicolons you have, and it is possible to do this with 0 strokes. I'll let you figure that one out. So this is an opportunity for you to recover points after having your confidence crushed by bridges. Okay, 150% is possible on this. Yeah, it's fine. I'm giving you an easy one. I'm literally giving you all a 9 out of 10 on this assignment to begin with. And you can go all the way up to 150%. Okay. I'll let you figure out the tricks for that one. Okay. Just don't copy and paste my code. You'll annoy me if you're just like, I don't know what this is. I'm just going to copy the professors and turn that in. Nah, don't do that. Don't just change the variable names. No, don't do that. It'll annoy me. Besides, the cheat checker removes comments and variable names anyway. So, all right. So let's talk a little bit about Markov chaining. You guys have any questions about Markov chaining? There's a lot of words in here. It's not too bad. A couple of questions that I've been given, and kudos to the students that ask questions rather than suffering silently and miserably staring at the screen for 8 hours rather than reveal that they are having an issue. One student was reading from disk and forgot that when you read from disk, the very last read you do will set the stream to be invalid. And so every time you read from disk, you immediately need to check to see if the stream is invalid. And if it is, you break out of it. If you don't, you're going to get the last element. It's going to be counted twice. So if you ever see a situation where like you're reading in words and it's just like hello world, and your vector contains hello world world, that's a sign that you read off the edge of the file and didn't check to see if you'd, all you have to do is say if not ends or whatever, and then break. You confused why you track the commas? What? Just think of comma as a word. Because, people use commas, right? So if I say hello world, comma, then world is followed by a comma. It's just basically treat a comma like a word. Yep. Yeah, so the way that you randomly regenerate the sentences, let's say that you've got hello, and 3 out of 10 times hello is followed by world, and the other 7 times hello is followed by Kearney. What you do is you roll a 10-sided die, and then if you get a 1 to a 3, you print out world, you go to that spot in the graph, and if you get a 4 through 10, you go to Kearney. Okay? So you have to use the same dice rolling system that I use, otherwise you're going to get different results. Okay. All right. So if you roll a 7, then the first edge has a weight of 3, so you subtract 3 off of it, you got a 4 left. The next one has a weight of 7, you subtract 7 from it, you get a negative number. That means that's your pick. Okay, so you have to look at the total outgoing edge weight. You roll a number based on the total edge weight, and then you go through each of the outgoing edges. You subtract off the weight of that edge until you have that number become negative, and then that's the one you pick. Okay, can you guys do this? I can't deal with silence. Like if you just sit there and just silently suffer, like I can't help you with that. You have to ask questions if you're worried about it. The graph is all set up for you already. There's already a vertex class. It's got a adjacency list. So every vertex has a list of edges that it's outgoing from it. And each edge holds a weight, how many times this word followed me, and it holds the word. So basically it's not the most efficient of data structures, because there's going to be a lot of redundant things. Like this probably should not be a word. It should probably be an index into the graph, right? So it just should be like my vertex connects to vertices 7, 9, and 12, right? Instead, it's holding strings instead of integers, which is inefficient, but whatever, it works. Anything else you need to say about it? Let's see. Read the file. Yeah, I've blocked it all out for you. Like I have pretty extensive notes on how exactly to do this. You're welcome. You don't have to really think about this one too much, I don't think. But there's usually something you need to do. Like how do I blah, and that's when you need to ask me, like, is there a command that will randomly generate a number? Yeah, right there. Yeah. Since I know we use it to track the index, but is the index the word? The hash table here maps from a word to an index in the graph. So the graph here is a vector of vertices. So it holds, let's say you've got 50 different words, the graph will be of size 50. Each vertex represents a different word in the corpus. The hash table, you pass it hello, and it returns, oh, hello is at index 17. It allows you to do fast lookups in the graph without having to iterate through every node in the graph to find out where hello is, you use the hash table for it. So you pass in hello, it passes back to you 17. This is an acceleration structure. It will make your code go much, much faster. You technically don't need to use the hash table. You can just write code that sucks if you want. But I don't recommend that. It will take noticeably longer to generate fake Alex Jones rants if you don't use the hash table. So the hash table you pass in world, it's like, oh, world's at index 15. And it's just the index, what it's returning, the size t, it's the index in this graph. Okay, so it allows you to quickly search the vertex to find where a certain word is. Okay. Does that make sense, Karate? Do you want to see how to use a hash table? Do you guys want to review on hash tables? I can do that. Yep. Do I want to delete this or not? Good night, sweet prince. Okay. No, my beautiful code. All gone. Okay. To track the index and the vertex. So it's calling graph.at. Yeah, so we've got a vector of vertices, you know. And so the size t that we're getting out of the hash is, so you're going to say graph.at that index that was returned by the hash table. Okay, and let's not call this hash, by the way. Hash. Yeah, whatever, it'll work. Technically, okay. There is a hash function in the standard library, but this should compile. Okay, so let's do this. Hash square bracket hello equals 5. What do you think that's going to print? You were counting the amount of words in the hash? No, you don't need to. Yeah, this is something called an associative array. So using square brackets is not good in this case. Always associative array. Yeah, it'll print out 5. So what this says is it associates a key and value. And this concept of associating a key and value is used a lot in computer science. If you ever do database work, keys use a key to search for something in your database. So, for example, social security numbers are often keys. You type in somebody's social, and then that is used to index the database, and you can pluck out somebody's record in order, you know, login time usually from a database using the key. Now, if you try to search for something that's not a key, like let's find somebody based on their address, if that's not a key in the database, then it's going to do an order in search instead. It's going to do DMV search, where it goes through every person in California, trying to find every person that matches your address. Okay? That takes a while. Even if, you know, you have a fast computer, there's a lot of people in California. You know what I mean? So what this is saying is the key that we're searching on is hello, and the value is set to 5. In this case is hello. We're searching on the key and printing the value associated with it. Okay? Print 5. What else can you do with it? Okay, one thing you have to be careful of is what if we print out what is the index of world? What is that going to print? What value is associated with world? There is none, right? There is none. Now, let me tell you about C++. This is a sharp edge in C++ that will cut you if you are not careful. A lot of people recommend not using square brackets at all with a hash table, because this will actually print out 0, I think. Double check. It prints out 0. Now, watch this. For every, this is going to be a pair of strings and size keys. So a pair is 2 values in one. It's like a struct that holds a dot first and a dot second. The dot first is a string in this case, because key type is string, value type is size key. So for every pair P in the hash table, this is how you print out a hash table, by the way. You normally don't do this, but it's useful to see what's in your hash table. So for every element in our hash table, see out the key, which is P dot first, and the value associated with that key, which is P dot second. Have you guys seen pairs before? Like the fruit? Okay. So it's this pair that we're talking about here is going to look something like this. It's going to look like, capitalize it so it doesn't conflict, but it'll basically be a string first and a size key second. This is basically the pair that we're talking about here. It's templated, obviously, but that's essentially what we're talking about. So when you have a pair, it's got a dot first and a dot second, and that's templated, and that's templated like that. So it's basically returning the key and value pair for every element in the hash table. Okay. So how many entries do we have in the hash table, do you think? How many values have we added to the hash table? How many key value pairs have we added to the hash table? Tomas is guessing 1. Does not trust his guess, though. Yeah. So this is the sharp edge. If you try searching a hash table in C++ this way for a key that does not exist, not only will it print 0, when it technically should probably throw an exception, it also inserts world into the hash table. So this actually creates an entry in the hash table for world and sets it to 0, then returns that value. So if we were to print out the entire hash table, we can see that world has been added to our hash table. So if you ever try searching your hash table for something that doesn't exist, it adds it for you. Most people recommend not using brackets with hash tables at all because of this sharp edge. I say it's okay because the syntax is actually really nice. You know, like this makes sense to me. You know, like, hey, the vertex associated with hello is at index 5 in the graph. That makes sense to me. Like, that's a beautiful syntax, you know. So if you want to use that, then what you have to do is say if hash dot contains world do this. So check to see if it exists first. And that's something you usually want to do anyway, right? Like if you're going to be adding, let's say you read in hello, and then the next word you read in is world. So hello's already been added to the graph. It's got some value. And then we're reading in world. We need to know if world exists or not, right? Because if world exists already, then we need to go into the hash table and find the address of world and then increase the edge weight between hello and world. The more times world follows hello, the more likely it is we're going to when we get to the node in the graph for hello, the more likely it is we're going to transition to world afterwards. So, but if it doesn't exist, then we need to add a new node onto the graph and make a connection between hello and world. So we typically need to do this anyway. Like it's very odd to just like print how many worlds have we seen, where did that even come from? Usually you want to do this anyway. So I write code sometimes with this. It does make me very nervous, right? So you can use instead the, can we add algorithm to code golf? The directions explain that. There's a list of rules for what you can do with code golf. Yeah. Okay, I think maybe not. I think maybe the merge and copy functions are not allowed. Maybe you have to write those yourself, if I recall. Okay. Yeah, I think you can't use merge. You can't use copy. You have to do all that yourself with no semicolons for max credit. Okay. So do you guys understand this? Do you guys know this function here? So if world is in the hash table, right? Yeah, okay. So C++ main.cc, and world is not in table. All right, and so now you noticed it did not add world accidentally to our code. So the use of square brackets with hash tables is definitely a bad and stupid design decision they made. It probably is one of the dumber decisions they've ever made. I don't want to go too far on that one because there's things like auto pointer and inheritance defaulting to private. Like there's some dumb decisions, back in the day. It's not like I could do any better. I've made all sorts of stupid decisions in the day. But yeah, this is just yeah. So use dot contains with it, and then it's perfectly safe. As long as you remember to use dot contains every time. Make sense? All right. And if you don't want to use square brackets, then we can come up here into CPP reference and pull up the unordered map class here. Unordered set map. And you can insert using that instead of square brackets. You can use dot at. Let's see. Yeah, so you can search for it on the key and it returns the value using dot at. Does it create an element? No. So if no element exists, then it throws an exception, which is probably how the square brackets should work. Square bracket is where is this square bracket? This is an ordered map. Where is the there we go. So returns a reference to the value that is mapped to a key, performing an insertion if the key does not already exist. So this is some fancy garbage right here. Yeah, and so do you guys understand the syntax though? You can associate a value with a key and then later on look up a thing. And it does so in order one time. So it's a very fast lookup. Unordered maps are one of those data structures you absolutely have to know. Okay? You absolutely have to know unordered maps or hash tables in general. Okay. So contains is true false. That's C++ 20 by the way. So it's new for some reason. If you're using an older version of C++, you're going to want to use find. Then find, if it's not in there, then it returns end like this. And so this is a more crufty, clunky version of doing contains. So you search for one, if it returns a pointer to the end, and remember the end is one out off the end. Right? That's one of the reasons why end is over here. Right? Because if it was pointing at the last element, then it would say, oh, we found that one. There it is. Right? So it has to be an invalid entry. Okay. So this is how you do contains prior to C++ 20. All right, no. You guys seem all pretty fine with that. So let's get back into the recursion thing. Okay. So merge sort. Basically, we check to see if we're the base condition. If we're not, then we split our array into left and right halves, and then we will merge. Then we recursively call merge sort on the left and right half, and then we merge the left and right halves together. And then that, at the end of the day, will give us a sorted array in provably optimal time. So, how many times can you divide an array in half before you hit the base condition? So if I have an array of size 16, how many times can I divide 16 in half until I get 1? What do you guys say? Put on the Jeopardy theme music. Yeah, very good, Thomas. 16 divides into 8, 4, 2, 1. So there's going to be 4 levels of division. Each one's kind of looks like a nuclear chain reaction of the particles flying out or something. I don't know. So the array of size 8 becomes 2 arrays of size 4, which become 4 arrays of size 2, which become 8 arrays of size 1. Okay, so that's 3 levels of division, I guess. And so one of the nice things about this is that you don't have to worry about your code crashing due to exceeding the recursive stack limit. Do you guys know why? Like let's say the recursion limit is 1,000 on our system. So let's say that we can call one of our functions, which calls itself, which calls itself, which calls itself. Let's say we have a recursion limit of 1,000. I've actually been on systems where the recursion limit was 32. And that's rough. Because then sometimes you just have a function calling a function, calling a function, calling a function, and your chain depth can actually get deeper than 32. So it's like, all right, I guess we're not going to do absolute value right now. We're just going to do it ourselves. We're just going to get the return value and multiply by -1 if it's negative. You know, like you start writing really bad code when you naturally hit a recursion limit like that. Yeah, let's say the recursion limit is 1,000. Why will we never exceed that with our merge sort code? Like the number of levels of division. Why will the number of levels of division, for all intents and purposes, never exceed 1,000? If we have 16 elements in an array, we're going to recursively call ourselves, we have a recursion depth of 4, right? We call merge sort on 8 and 8, and then 8 calls 4 and 4, and 4 calls 2 and 2, and then 2 calls 1 and 1. So the maximum depth is 4 on a size 16. The integer could be 2 billion. Yeah, so it has to do with logarithms and exponents, right? So in order to exceed the maximum depth limit of 1,000, how big, let's do this as an exercise. How big must our array be? All right. If our recursion limit was 4, then we would hit that with an array of size 16. If our recursion limit was 5, we'd hit the limit with an array of size 32. If our recursion depth, do you know what I mean by like recursion depth? Like how many times f can call f, which can call f, which can call f, before we segfault? So if our maximum depth is 6, then what was that? 32 or something? Yeah, it's 2 to 1,000. 2 to 1,000. If our recursion limit is 1,000, which is not unreasonable, then 2 to 1,000 is 10 to the 300th power. So that means our array has to be, that's the size of the array. The size of the array would have to be 10 to the 300th power in size in order for us to exceed a recursion depth limit of 1,000, which isn't even that big. A lot of times they set it small like that just as a convenience, so your code crashes sooner when you have an out of control recursion. Do you guys understand how big 10 to the 300th power is? You know? Like, it's pretty big. Yeah, 2 to the 32nd is already pretty big. That's 4 billion, elements. 4 billion elements in an array. 4 billion. That's a giant. That's like half the people on Earth. You're gonna hold all the people on Earth, and you want to sort all the people on Earth. You need a recursion limit of 33. Okay. So, is there even that many stars? No. The number of stars is like 2 to the 60th, 70th, 80th, something like that. Something like that, or 10 to the... How many stars are there? There's 10 to the 10th, 12th in our galaxy. So something like 10 to the 20th or 10 to the 30th, something like that. So, not anywhere near the number of stars in the universe. Yeah. Like, 10 to the 300th power is an unbelievably large number. It's bigger than any possible thing. Yeah. All right. So every time we divide, we go half in size. And so anytime you hear halving or doubling, that should tell you the answer is either going to be exponential or logarithmic, right? So logarithmic is the opposite of exponential. 2 to the n, the opposite of 2 to the n is log base 2. Yep. At each level of division, we do an order n merge, because we're basically at every level that we divide down, we're going to be going across it and zipper merging all the size 2 ones together. Then we go up a level and merge all the size 4 ones together. So at every level, we're doing order n work. So the total work is order n log n, and that's provably optimal. Okay, so it looks kind of like this. So you take phase 1, you split everything down into size 1 arrays, and then you zipper merge them together. So, and at every level, you have a sorted array, and so you can always merge sorted arrays very easily. And so you just consistently merge the sorted arrays together over and over again. Okay. So when does it ever sort? When does it ever do the sorting? It just always has sorted arrays, and it always merges them together. When does it actually do the sorting? So with selection sort and bubble sort, you're like moving things around, right? When does it actually sort? When does it ever put things into sorted order? The merge isn't really sorting, though, right? It's just merging. If I hand you an array of size 100 and an array of size 100, and they're sorted already, all you have to do is just put them together so that they're in sorted order, right? You're not actually moving things around. You're not actually sorting anything. You're just, saying, okay, here's a sorted one, here's a sorted one, I'm going to put them together, and it's still sorted. When does it ever actually sort? When do you ever put things in order to begin with? Because for merge sort, you can think of it like this. Assume that I have 2 sorted arrays. If you give me 2 sorted arrays, I will give you a sorted array combining all of those elements. Where did this sorted array come from? Merge pseudo sort? Right? Yeah, the merge doesn't actually do any sorting. It just puts together 2 things that are already sorted. So think about it. If I told you, it's like black magic, right? If you give me 2 arrays that are sorted, I will put them together in sorted order. Well, where did the sorted arrays come from? Well, that came from another iteration of that, where you gave me 2 smaller ones and I handed you a merged one. Where does the sorting come from? Doesn't it have to sort the sorted arrays? Nope. It doesn't. If you hand me 2, 4, 5, 6 and 1, 2, 3, 6, all I do is I just look at the first element of both and I say, okay, pick off the first element here and pick off the first element here and the second element here. And then that guy, and that guy, then that guy, then that guy, then that guy. Right? I'm not actually sorting anything. I'm just combining them.
I'm combining two already sorted operations. If these two things were not sorted, I could not do this. The sorted merge would not work. So where does it come from? Where does the fact that every level of merge sort requires you to hand me merged, or that you need to hand me sorted arrays? Where does the original sorting come from? What's the OG sorted array? What's the base condition? It's the end of our recursion here. Where does the original sortedness come from? It's a philosophical question. Yeah, all the arrays of size 1, they're sorted. This is a sorted array. That's a sorted array. That's a sorted array. That's a sorted array. These are all sorted arrays. So that concept of being sorted comes from the fact that a solitary element is sorted. And then you just can put them together in sorted order, you know? And so you just zipper merge two vectors of size 1 together, and you get a sorted array. So this is sorted, that's sorted. When you zipper merge them, that's sorted. That's sorted, that's sorted. You zipper merge them, that's sorted. That's sorted, that's sorted. You zipper merge them, that's sorted. That's sorted, that's sorted. You zipper merge them, that's sorted. So the property of being sorted comes from the base condition, the root, the philosophical origin of the sortedness of the array comes from the fact that an array of size 1 is sorted. And then after that, you just put them together in sorted order. You don't have to hunt around for who's the biggest element, who's the smallest element. Nope, don't have to worry about that. Yeah, sorted 1. Okay. So, yeah, code golf this is our second code golf assignment. But this one, you're going to be graded on semicolons rather than total character length. Okay. So remember, you have to dress the part for doing code golf. When you're doing code golf, you cannot use mobile telephones, t-shirts. Your shoes should probably be brogues or something dressier than that. Boots are pretty much not acceptable. Black socks are preferable to white socks, probably. But, you know, if you have to, you can wear the white socks. Okay. Belt is also preferred. And if it's evening time, it's customary to wear like a jacket or something like that. So you have a little bit more formality for the code golf course. Okay. So, what if your shirts only have collars and sleeves? Then you're good, because all shirts must have collars and sleeves. You're not allowed to wear a t-shirt while doing code golf. It's the dress code for code golf. Okay. Okay. Yeah. So the cheat checker will definitely be run on this assignment. Don't turn in my solution. Also, you can't use merge or copy. Did make for writing it very quickly in class today, but you have to do that yourself. Make sure you're also doing merge sort. So a lot of students end up doing some other sort, like selection sort or something, where they loop over the whole thing and pick out the smallest element and put that in. Like, nope, can't do that. Can't do that. You take my solution and attempt to make it shorter, sure. Yeah. Just don't turn my solution in. And also my solution used merge and copy, which you can't use. And try to do it with as few semicolons as possible. Okay. So normally I do trophies on this. I might still do it. So one trophy is going to be awarded to the student with the minimal code length. One trophy, one trophy for minimal characters. One trophy for the fastest running time, and one trophy for the most unique solution. Each of these is an extra letter grade. Okay. So if you want to minimize the total number of characters, that's a letter grade. If you have the fastest running time implementation, it's a letter grade. If you have a unique and ugly or a beautiful solution, letter grade. Okay. And so when you submit it on Canvas, there's going to be a place where you put your semicolon count. And then if you think you're up for any of these trophies, post number of characters, post your running time on like 1 million elements or something, and And if your code's unique, then explain why. Okay. Lost Vex credit. Recover from bridges. Get your confidence back. Do you think you guys can write a zipper merge on your own without needing the standard library? Given two arrays, find the smallest element of the front two, put that in, move the person you're looking at one to the right. Define colon, semicolon. Yeah, the rules say you cannot use hashtag defines to eliminate any semicolons, unfortunately. So you can use hashtag defines, but they cannot be used to reduce the number of semicolons you have in your code. But good idea. I like that. Look very carefully at the rules and exceptions. It's like when you go into the Willy Wonka chocolate factory. You know, you gotta read the terms and conditions very, very carefully before you commit to a course of action. If you tried defining semicolons away, then you would be in violation of the rules. You get nothing. Good day, sir. If your code is bad, will a bunch of little people berate you via song? Yeah, that's the whole idea. There you go. Yeah. CD into Mergesort golf. All right. So yeah, tons of extra credit. Yeah, there is a check to see if you are leaking memory. You're probably not going to, because you're probably going to be using vectors. But if you wanted to, you could use arrays if you wanted. If you have any warnings in your code, when compiled with -wall and extra warnings, then you gain an additional stroke penalty. If you can disable the warnings in your code, go for it. There are pragmas that can turn off warnings, so if you turn off the warnings, you won't be penalized. Cheating, you get a 0, obviously. Okay, here we go. Here are the rules. There's a lot of rules. Okay. You can only write code between the lines of begin golf and end golf. Okay. You cannot change anything in main. You can't change anything outside of that section. You can use preprocessor directives, but only to improve readability. You cannot do what Vargas wanted to do and get rid of semicolons. Sorry, can't do that. It's too easy. You cannot use any STL or standard library classes or functions, except as noted below. Okay. So, here are the data structures you can use. A C-style array, a C++ style array, or a vector. That's it. You cannot use a hash table, cannot use sets. Should be very easy. Insert everything into a set, and call it a day, right? Because they're all sorted. You can call any of the standard member functions on arrays and vectors, .size, .at, all that stuff. That's all fine. Otherwise, you can use no functions instead. No copy, no merge, obviously not sort. Okay. You can use iterators and pointers on the data structures, obviously. You can use the comma operator. Do you guys know about the comma operator? You guys want to see some black magic? You guys have probably seen the comma operator before in terms of variable declarations, right? But check this out. Is 0 true or false? It's false. Okay. So, if you guys have ever used Python, this code will probably confuse the hell out of you because it works differently in Python. Is 20 true or false? It's true. So, is this code going to print hi or bye? Place your bets now. Operators are standing by. This code compiles, by the way. There's a warning, rather obviously. But, both? Pretty sure it can be both. If else is mutually exclusive. So, let's compile it. Hi. Why? Well, the way the comma operator works is that when you evaluate an expression with the comma operator, the expression evaluates to whatever is on the right-hand side of the comma. So, if we were to see out x comma y, it'll print 20. Okay. So the comma operator basically returns whatever's on the right-hand side of the comma. It's not an or. It's not an or statement. If I did it this way, then you'll see it prints out by. Because 20 comma 0 evaluates to 0. 0 comma 20 evaluates to 20. Okay. So the comma operator, I'm not going to explain to you how this can be used to take you down to 0 strokes. It can be used to take you down to 0 strokes. Okay. Does the first term even need to be there? No. The first term here does nothing. It does absolutely nothing. That's why I'm getting a warning. It does nothing. But check this out. I'll give you one clue. So you see how x and y both got incremented? They were 0 and 20. When I printed out the value of x and y, I got 1 and 21, right? So I was able to do this increment without using a semicolon. Okay, notice how the warning went away. Right? So this is some obscure black magic BS, by the way. Don't write code like this. But for code golf, kind of fun. All right. So yeah, you can use it. You can use it to hide commands and things like that. I'm not. I don't want to go into too much detail because it's a lot of extra credit, but might spark some creative juices in your brains. Okay. Hope that was illuminating and horrifying all at the same time to you. So the comma operator is part of an expression, and whatever is returned from that an expression is anything that can be put into smooth parentheses, right? A statement is anything that ends in a semicolon. And an expression is anything that can be embedded into statements with parentheses. And so the comma operator can be put into expressions. Okay. All right. Sounds like one of those job security tips you give, yeah. You put that code in there, and and no one will be able to figure it out. All right, you may not make new functions. Oh, you can't use a helper function. Never mind. Yeah, all right. Well, there you go. So you cannot make new functions or lambdas for that matter. You can change the signature of Mergesort, but you cannot modify main. So everything has to be in a single function, no helper functions. Originally, when I did this assignment, I allowed helper functions, and then students figured out very clever ways of cutting the semicolon count down to 1 using that. You can use the ternary operator. Ternary operator is allowed. Do you guys know the ternary operator? It's like an if statement. The one you use for Facebook and Twitter. Yeah, so it's an expression version of an if statement, right? So you say some expression question mark, and if the question mark is true, the thing before the colon gets evaluated. If the question mark is false, then the thing after the colon is evaluated. But the nice thing about the ternary operator is you can embed them inside of other commands and things like that. So there's probably something there too you can use. No digraphs or trigraphs, which are things that look like this. They're not in the language anyway in C++ 17 and above. They got rid of them, but have you guys ever seen digraphs or trigraphs before? We're just going through like the rubbish pile of C++ at this point. Whew. All right. All right. So, what do you think this code's going to print out? Here, let's make it Nani? There. What do you think this code's going to print out? No clue? Take a guess. Take a wild guess. Got a quote? Double quote? Nani? What do you think? Intuitively the same string? Why is there a warning? Why is there a warning? There's a warning on this. Bell, have you seen trigraphs before? I have a feeling that some poor 40 student tried to print this out at some point. Yeah, that poor 40 student would be me, because I will type this occasionally. So yeah, let's compile this. And let's compile it first using C++ 20. And we'll see that we get Nani. Well done. Guerrero, you're correct. Nobody else had the, mental fortitude and courage to just say, shouldn't it just print Nani? Question mark, exclamation mark. All right, so what is that going to print? Too easy. I'm compiling right now in C++ 20 mode. Remember, trigraphs were removed in C++ 17. So the compiler warns about them, but it doesn't do anything. Both lines? Yeah, okay. All right, let's do that. Seems fine. So there's our command, and then if we compile this, g++ scud equals C++ 11, then it prints out Nani vertical slash. Why? That's a great question. So, IBM is the reason why. For whatever reason, IBM fought with the standards committee for decades to keep trigraphs in C++. And you might be asking, what is going on here? Why is question mark, exclamation mark, vertical slash? Right? Anyone want to ask why? That's a vertical slash. Well, back in the 70s, not every keyboard had a vertical slash character on it. So, they added support to type in certain special characters so that people who didn't have a vertical slash could type C++ code. Because you needed a vertical slash to do an OR, right? So what is this code going to print? IBM wanted to keep it for nostalgia. I think they had code that used trigraphs and they just didn't want to have to go through millions of lines of old code from the 70s and 80s and fix them. And so they fought tooth and nail for decades to keep this BS in the C++ language well after people had a vertical slash on their keyboard. You know what I mean? Just because they didn't want to have to go back and refactor old code. And they were finally gotten rid of 4 years ago. So, legacy code, yeah. So, so lazy for not wanting to do an easy find and replace. Right. All they had to do, like all you have to do is go through your code and be like, all right, every time there's a trigraph, replace it with the thing that it corresponds to. It's once. You know, it's not even, you don't even need a programmer looking at it. You know? So what is this code going to print? Where's iota? Numeric. I'm giving you guys some horrible, horrible things right now. Okay. Does it have to take a value? Yes, it does. Okay. So, yeah, code compiles just fine. Yeah, keyboards did have greater than and less than before they had curly braces. So you're talking about backwards compatibility with keyboards from an era before they had the standard set of keys on them. So you're talking really, really old, because we've had vertical slash like that keyboard layout is garbage. It's amazing. Huh, maybe there is no vertical slash on that one. There's no curly braces either. Yeah, okay. So that's, there you go. So it's got semicolon, it's got colon, it's got an upside down question mark, right side up question mark, which is way up by 0. I don't know if you guys can see this. Let's zoom in here. It's got like the accent characters. I bet this is a foreign keyboard, actually. It's got this looks like a French keyboard to me, actually. Yeah. Okay. Oh, there's the curly braces. There's curly braces. There's square brackets. Less than and greater than. Less than or greater than. I don't see those on here, actually. Interesting. Yeah. In Lucerne. So that's a Swiss computer. Let's see. Does that have sounds of the typing? Okay. Let's take a look at this. Yeah, so they got curly braces, square brackets, greater than, less than. Looks pretty similar to what we got today, really. The tilde key isn't up there. Otherwise, yeah, this is pretty much standard. And this is, the OG keyboard. So, yeah, so that's, there you go. That's the thing. Do you guys know about IOTA? Do you guys know about IOTA? I don't know an iota about IOTA. So it initializes this array with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm printing all the elements in the array out. And yeah, so question mark, less than is open curly brace, question mark, greater than is closed curly brace. So I got my braces replaced here. The vertical slashes are replaced with that. Let's see, what else can we do? Square brackets. I apologize so much for today. Yeah, compiles just fine. Look at this code. Look at it. Look at it. My beautiful code. Look at it. That makes an array of size 10. Yeah. Yeah. Does it not like that? Doesn't work with the preprocessor. No, it works fine. So X or Y is false now. Do you see that? See what I changed? I hashtag defined true to be false. Poor Clang. Clang is just dying here. So I defined true to be false. Define true to be rand modulus 2. Vim is dying. Look, Vim doesn't understand this. Vim doesn't know that these are supposed to be curly braces. Lord. Yeah. Let's see here. There we go. We just got true a bunch of times. Yeah, so some of the times X or Y is true, some of the time X or Y is false. As you can clearly see here, X is sometimes true. This is one of the greatest lectures I've ever given in my life. Clang D is just having a heart attack. Vim is having a stroke. Nothing makes sense. Sanity has been abolished. Yeah, so every time we use the word true, it's actually going to flip a coin as to whether or not it's true or false. The question mark, exclamation here turns into a vertical slash. Yeah, so yeah, it's Nani vertical slash. Yeah, yeah. So there you go. If you want to write the absolute worst code you can ever think of, this is a pretty good candidate here. Copy main.cc public. This is not the worst code in the world. It is a what? It is a tribute. Okay. .cc. So you can grab a copy of that if you want. We got 4 minutes left. You have to actually do merge sort. If you have commented out lines with semicolons, they do count actually. So delete any of your commented stuff out. You can use plus minus minus. You can't mess with our stroke count calculation. So there's a scoring program that will tell you what your score is. You can't screw with that. If you knew memory, you must delete memory if you want to do that. Okay, so minimum strokes. Yeah, we're not going to do that. We're going to do minimum character count. That's more interesting because you're already minimizing strokes. Minimum character count. Add up all of the characters between begin golf and end golf. And report the result on canvas. Comments count. So maybe delete them. Okay. Oh wait, I already have minimal character count. Fastest running time. Wait, what was the other one? No. Minimum character. Fastest running time. And then the third one is weirdest. or most unique. If you think your code is especially clever or weird or ugly, submit on Canvas why you think it is, and I will consider it for this trophy. Okay. And each student can only get one trophy in order. Okay. You guys understand? So if you make a makefile, then you're more than welcome to use trigraphs and things like that. Because if you use a makefile, then you can change the standard you're using. Will there be participation trophies? That's kind of the unique one. Deploy homework, CSI 26, merge sort. Okay, so there you go. Have fun with that. Get Markov chaining by Thursday, and have fun. So, hopefully, so what you're going to experience with this assignment is you're going to rewrite probably merge sort over and over and over and over and over and over again. And by the time you've rewritten it about 10 times, you're going to understand merge sort really, really well, which is why I do this assignment. Because as we saw from our lab time today, nobody got merge sort written. It's actually very easy to write algorithm. Am I at the base condition? If so, return. We're done. If not, then sort the left half, sort the right half, and then merge the sorted results together. That's it. It's really, really small, simple to write, easy to code, and you're going to redo it probably a half dozen times to get your semicolon countdown. So it's a good learning process. You know, by repetition, you'll come to understand it. Okay, so that's it for today, guys. If you have any questions, post on the Help Center, hopefully before tomorrow night, because I might go to bed early. I don't know. All right, see y'all.